Alright, so we are on the third and final module, and within the module 3, I'm going to be talking about the GLM, and within the GLM there is MRC and ANOVA. MRC focuses on the measures of association, whereas ANOVA focuses on the measures of difference. MRC can be converted into ANOVA from a correlation to a t-statistic. That connection, or bridge, is known as the point biserial correlation. Within MRC, the objective is to learn more about the relationship between several independent or predictor variables and a dependent or criterion variable. It allows the researcher to ask and hopefully answer the question, what is the best predictor of? Whereas ANOVA takes multiple means and compares them. There are similar assumptions underlying the models. They both offer some similar hypothesis tests, omnibus tests, and simple effects, and because the GLM is an independent linear model, they both require linear or additive effects, and they both focus on understanding variance, but do so in a different way. And I will talk about that later in the presentation when I go into the diagnostics. So when we conducted an MRC with 3 predictors, I chose X4, X5, and X6 for Module 3 data, and the first thing I did was look at the regression coefficients, the betas and unstandardized coefficient column, or the sig or p-values. As Gary King said, standardized coefficients are generally more difficult to interpret. Do not add any information that may help to compare the effects from different explanatory variables and may add seriously misleading information. As the table shows, X5 and X6 are significant predictors in predicting outcomes of Y1. X4, however, is not significant and not a good predictor in predicting Y1 for the hypothesis. So before I go into diagnostics for MRC, I want to emphasize that MRC's diagnostics focuses on residuals and requires covariates, such as X1, X2, and X3, where the variance would be attributed to the individuals. And ANOVA's diagnostics focuses on error and requires factors, where variance would be attributed to the group. For MRC diagnostics, I chose X1, X2, and X3 to be the independent variables and Y1 to be the dependent, and I'm trying to predict Y1 from X1, 2, and 3. So within this bivariate plot, there are no extreme outliers that are in the matrix plot. This violates the assumption of MRC in that the relationship between X and Y is linear or rectilinear because, for example, X2 on X3 do not have a direct linear relationship. First, when looking at the coefficient table, it's important to look at the collinearity statistics and determine if there is multicollinearity by looking at the VIF factors. There does not seem to be a problem of multicollinearity in the analysis because it is within the normal range. In regards to the parameter estimates, the betas are acceptable because they are between -1 and 1. And all of the significant values are above 0.05. Which brings me to the conclusion of failing to reject the null. It's also important to mention that X1, X2, and X3 all account for 24% of the variability of Y1. As for the model summary table, the Durbin-Watson statistic is close enough to 2 that we can say that the analysis does not violate the assumption of independent residuals. As Gary King said, one should not make too much of any interpretation of the residuals from a regression analysis. Sometimes outliers can be overly influential, which is why we should examine the residual statistics as well as the Cook's distance and leverage variables to see if there are any influential cases in the dataset. Cook's distance is basically how influential and how much leverage has on betas in the standard error of the betas, and leverage is the extent to which any single observation in our prediction model affects the predicted values. Our mean leverage is 0.10, and I'll use 0.20 to see if there are any influential cases in the dataset. When looking at the dataset, there are 3 numbers that are greater than 2, and thus are 3 outliers that need to be deleted, and then another analysis with deleted outliers needs to be run in order to compare the analysis 2 to the result of analysis 1. So when looking at the bivariate plot for analysis 2 with the 3 outliers deleted, there are no outliers concluded in the matrix plot. But when looking at the graph, it's obvious that the new analysis violates the assumption in MRC that the variance is constant for all values of x. The plot is heteroscedastic because it has a lot of variance between the residuals. So as you can see, here's the mean, and there is a lot of variance between the residuals here versus here versus here. So it's heteroscedastic. As I said before, VIF values should be less than 4, so there's no problem of multicollinearity in the second analysis, as was the same in analysis 1. The sig values are all above 0.05, so we still fail to reject the null. And betas are all accepted as well. The sig values, x1, x2, and x3 now account for 21% of the variance of y1, whereas before it was 24%. Our Durbin-Watson statistic should be close to 2, but it is at 1.078, which is far away from 2 and thus violates the assumption of independent residuals. Our mean leverage is now 0.0824169, and I will use 0.16 to see if there are any influential cases in the data set. When looking at the data set, there are still 3 numbers that need to be deleted due to outliers. But with the small data set of n equals 30 and this second analysis with n equals 27, it's not worth it to run another analysis with the deleted outliers. So another assumption within the MRC is that the mean error or residual should equal 0. And as you can see, the mean error equals 0 and thus does not violate the assumption of mean errors equaling 0. So are the residuals normally distributed? The histogram seems to be close enough to a bell-shaped curve, but is not typical. The probability plot shows that the data set is normally distributed because it follows a straight line. If you can find a straight line, then you can conclude that there is a linear relationship between the 2 predictors. x1 and x2 are negatively correlated, so it does violate the assumption of linearity in MRC, the assumption that the relationship between x and y is rectilinear. There is a negative relationship between x1 and x2, and thus violates the assumption of linearity in MRC. When residual plots suggest normality, it sometimes may be due to the skewed y variable. Our skewness value is negative 0.059, which if using the skewness value of negative 1 to negative 0.05, then we can conclude that our skewness value is moderately skewed because it is greater than negative 0.05. Our kurtosis value is negative 0.813 and is within normal range, but we can conclude based off of our skewness value and the histogram that the y variable is negatively and moderately skewed as well as not normally distributed, thus violates the assumption of normality. It may seem odd that a procedure that compares means is called the analysis of variance, but it's derived from the fact that in order to test for statistical significance between means, we are actually comparing or analyzing variances. It's accomplished by analyzing the variance by partitioning the total variance into the component that is due to the true random error within the sums of squares, and the components that are due to the differences between the means. The latter variance components are then tested for statistical significance, and if significant, we reject the null of no differences between the means and accept the alternative hypothesis that means are different from each other. So within the descriptive statistics to table, the sample size is not equal for each condition, thus violates the assumption of identical sample sizes, which makes the data unbalanced. In Levene's test of equality of error variances, we want the p-value to be greater than 0.05. Our sig value is 0.375, which means there is no significant difference, which equals equal variance, which is good because we don't want to find a significant result. So it does not violate the assumption that the distribution of errors is normal. When looking at the test of between subject effects, The F value for F1 is 0.029, and F2 is 2.308, and for the interaction, it's 0.033. So when looking at the F table online, the critical F values are noted on the slide here. What we want to know is, are the F values bigger than the critical F values? So are any of these values bigger than any of these values? The answer is no, which brings me to the conclusion to fail to reject for the null for F1, F2, and the interaction. And the same is found in the significance column. As you can see, none of these values are less than 0.05. So we're still going to fail to reject the null. So this ANOVA plot tests for homoscedasticity, where predicted values are on the x-axis and the residuals are on the y. The lines show the means of the values of y, and thus it is clear that the dataset violates the assumption of homoscedasticity, and thus shows signs of heteroscedasticity because the distance from the mean and the residuals are not similar. See? So, for my made-up data and the results in the hand calculation, my data proved to fail to reject the null. But, as Cortina said, we never accept the null. It is unacceptable to conduct a standard significance test and conclude from p is greater than 0.05, or p is less than 0.05, that no effect exists. There are simply too many alternative explanations, which is something to take in consideration when making conclusions about whether an effect exists or does not. After doing the ANOVA hand calculations, I put the data into SPSS, and the results were identical to my calculations. If you wish to take a closer look at my calculations, you may stop the presentation. But as for now, this is the end of my Module 3 and the end of my first statistics course in graduate school. See you in regression.